In the vast darkness beyond the night sky, size becomes a difficult thing to hold on to. Distances stretch until comparison breaks down. Objects grow so large that familiar words begin to soften at the edges. And a question that sounds simple, at first slowly reveals how little it wants to be pinned down. What is the biggest thing in the universe? Welcome to the Sleepy Scientist. If you enjoy drifting through questions like this, you're very welcome to subscribe and join these quiet explorations. And if you feel like it, share where in the world you're listening from tonight. It is always grounding to know how far these thoughts travel. At first glance, the question feels straightforward. Bigger than planets, bigger than stars, bigger than galaxies. It sounds like a matter of finding the largest object and pointing to it. Yet beneath that simplicity lies something deeply unintuitive. Because in the universe, size is not a single quality. It depends on what is being measured. Mass or distance. Extent or influence. Matter or emptiness. And the answer changes depending on which lens is used. For most of human history, size meant something physical. How tall a mountain felt when standing below it. How wide an ocean seemed when crossing it. Even now, bigness is tied to effort, presence, and visibility. But space does not cooperate with those instincts. Beyond Earth, kilometers thin out. Beyond the solar system, they lose usefulness entirely. Structures stretch across distances so vast that numbers stop anchoring meaning and begin to dissolve into abstraction. Astronomy responds to this not with a single definition, but with layers. Objects give way to systems. Systems give way to patterns. Patterns give way to limits of observation. Some of the largest things in the universe are made of matter. Others are shaped by gravity. Others still are defined by absence, by regions where very little exists at all. Size becomes less about edges and more about context. Tonight's journey is not about crowning a winner or memorizing extremes. It is about slowly approaching a question that sounds simple, yet grows stranger the longer it is held. What it means to call something the biggest, why that answer keeps shifting, and how the universe quietly resists being reduced to a single scale. Settle in. Let size lose its sharp edges, and allow the question to unfold at its own pace. What is actually the biggest thing in the universe? Most people grow up ranking things by size. The tallest building, the longest river, the largest animal to ever live. It is a comfortable habit, learned early, reinforced often, and rarely questioned. Bigger feels objective. Bigger feels measurable. Bigger feels like the sort of question that should have a clean answer, preferably one that fits neatly into a sentence and stays put once it is found. In everyday life, this instinct works well enough. A house is bigger than a car. A city is bigger than a village. A mountain is bigger than a hill. Size feels like something that can be confirmed by stepping back and looking. Even when numbers are involved, they remain tied to intuition. Meters, kilometers, tons. These are scales that still connect to human experience. They may stretch imagination, but they do not break it. So when the question is asked, what is the biggest thing in the universe? It sounds like more of the same. Surely there is a largest object, something so vast that everything else falls beneath it in a neat cosmic ranking. A winner at the top of the list. The universe, after all, is full of enormous things. Stars larger than entire planetary systems, galaxies containing hundreds of billions of suns, structures so wide that light takes millions of years just to cross them. Surely one of these must qualify. Yet the moment the question is held for longer than a passing thought, it begins to shift. Because in astronomy, size does not mean just one thing. It never has. And the universe is remarkably uncooperative when asked to line itself up for comparison. The first problem is definition. What does biggest actually refer to? Is it length, measured from one side to the other? Is it mass, the amount of matter something contains? Is it volume, the space something occupies? Or is it influence, how far its gravity or effects reach? On Earth, these ideas usually overlap. Larger things tend to be heavier. Heavier things tend to have more influence. In space, those connections loosen and sometimes disappear entirely. A star, for example, can be enormous in size while being relatively light by cosmic standards. Some of the largest known stars are spread thin, their outer layers puffed outward, making them vast in diameter but surprisingly diffuse. Meanwhile, much smaller objects can outweigh them entirely. Size and mass part ways quickly once gravity and density enter the picture. Then there is the question of boundaries. Where does something begin, and where does it end? This sounds trivial until trying to answer it in space. A planet has a surface, but its gravity extends far beyond it. A star system has planets and dust, but also distant clouds of debris that fade gradually into interstellar space. A galaxy glows brightly at its centre, yet sits inside a much larger halo of invisible matter that stretches far beyond what can be seen. Even emptiness refuses to cooperate. Vast regions of space contain very little matter at all, yet still form part of larger structures. These regions influence how galaxies move, how matter flows, and how the universe evolves. They are not objects in the everyday sense, but they are not nothing either. Size begins to depend not only on what is present, but on what is missing. Perspective adds another layer of complication. From nearby, a galaxy feels immense. From far enough away, it becomes a dot in a web of thousands of others. Zoom out again, and entire clusters blend into patterns. At each scale, the idea of biggest resets. What once felt dominant becomes just one piece of something larger. Astronomy has learned to live with this discomfort. Unlike many fields, it rarely offers a single final answer. Instead, it works with models, ranges, and context. Ask astronomers for the biggest thing in the universe, and the most common response is not a name, but a pause, often followed by a careful clarification. Biggest in what sense? This habit has become something of a quiet joke within science. The phrase "it depends" appears with surprising frequency in serious research papers, not because scientists are unsure, but because the universe itself resists being simplified. Reality, especially on the larger scales, prefers conditions over categories. Consider distance. The universe contains separations so vast that ordinary units become meaningless. Kilometers grow unwieldy. Even astronomical units, the distance between Earth and the Sun, quickly lose usefulness. New measures are introduced not for elegance but for survival. Ways to talk about separation without drowning in zeros. Size becomes tied not to objects alone, but to how far apart things are allowed to be while still belonging to the same structure. Influence complicates things further. Some objects extend their effects far beyond their visible edges. Gravity does not stop at a surface, it fades gradually, reaching outward without a clear cutoff. A massive cluster of galaxies may dominate the motion of others across immense distances, shaping regions of space far larger than its bright core would suggest. Is the cluster defined by its light or by its pull? Time also plays a role. Some of the largest things in the universe are not static. They are processes unfolding over billions of years, structures that form slowly, stretch gently, and change shape as the universe expands. Size becomes something dynamic, not fixed. A thing can grow larger without gaining matter, simply because space itself is changing. This is where the familiar instinct to rank and compare begins to falter. Lists require stability. Rankings assume agreement. The universe offers neither easily. Instead, it presents overlapping answers, each correct within its own frame, none fully complete on their own. Yet this is not a failure of understanding. It is a deeper kind of clarity. The question itself is revealing. By asking for the biggest thing, the human mind exposes its desire for anchors, for a sense of scale that can be grasped and held still. The universe responds by showing that scale itself is layered, relational, and often soft around the edges. There is a quiet humour in this exchange. Humanity looks outward and asks for the biggest thing imaginable. The universe responds by gently asking, what exactly is meant by that? It is a conversation that has played out many times before, and will likely continue as long as curiosity survives. So the value of the question is not found in rushing toward an answer. It lies in slowing down enough to see why the answer keeps shifting, why objects turn into systems, systems into patterns, and patterns into limits of observation. Why size at the larger scales becomes less about dominance and more about context. The question is not wrong because it is foolish. It is wrong because it assumes the universe owes a simple reply, and in discovering that it does not, something quieter and more interesting begins to take shape. When the word big is used in everyday life, it usually feels self-explanatory. A bigger house takes up more space than a smaller one. A bigger vehicle weighs more, carries more, and is harder to move. Size, weight, and presence tend to travel together. On Earth, these qualities overlap so reliably that they begin to feel interchangeable. Big means large means heavy means important. The universe quietly breaks that habit. In science, and especially in astronomy, size splits into several different ideas that do not always agree with one another. Physical width is one of them, but it is far from the only one. Mass, volume, extent, influence, duration, and even visibility all offer competing answers to what it means for something to be big. None of them are wrong. They are simply measuring different aspects of reality. Physical size is the most intuitive place to start. This is the edge-to-edge measurement, the span from one side to the other. It is how a ruler or tape measure would describe something, if such tools could survive the vacuum of space. A star can be measured this way, so can a galaxy. The diameter becomes the headline number, yet even here simplicity fades quickly. Many cosmic objects do not have sharp edges. They thin out gradually, fading rather than stopping. Where exactly does measurement end? Mass introduces a different kind of bigness. Mass is not about how much space something takes up, but how much matter it contains. Two objects can share the same physical size and have radically different masses. A balloon and a rock make this clear on Earth. In space, the contrast becomes extreme. Some objects that appear enormous are surprisingly light for their size, spread thin by internal forces. Others are compact, dense, and heavy beyond intuition. This separation between size and mass matters because gravity cares about mass, not appearance. A small object with enormous mass can dominate its surroundings far more than a much larger but lighter one. In this sense, big can mean powerful rather than wide. It can mean influential rather than visually impressive. Volume adds yet another layer. Volume measures how much space something occupies, regardless of what fills that space. A region of hot gas stretching across millions of light years may contain less matter than a single galaxy, yet its volume dwarfs it completely. If big means taking up room, then emptiness can easily win. This idea often feels counterintuitive because emptiness does not look like much. Yet in the universe, empty space is not meaningless. Vast regions contain only a few particles per cubic meter, yet they shape the movement of galaxies, channel matter into filaments, and influence how light travels across cosmic distances. Absence becomes part of structure. Nothing, in large enough quantities, starts to behave like something. Extent is related but subtler. Extent asks how far something reaches, not just where it is concentrated. A galaxy's bright disk may look compact, but it sits inside a much larger halo of unseen matter that stretches far beyond what telescopes reveal. The visible portion is only the densest core of a much broader presence. If size is defined by reach, then what cannot be seen may matter more than what can. Visibility itself complicates things further. Astronomers do not observe the universe directly. They observe light, and sometimes other signals, that survive long journeys to reach detectors. This means that what is seen depends on what emits light, what blocks it, and what instruments are sensitive enough to detect. Some of the largest components of the universe do not glow at all. They reveal themselves only through subtle effects on visible matter. If something cannot be seen easily, does that make it smaller or simply harder to notice? Everyday experience rarely prepares the mind for this. On Earth, visibility and presence are closely linked. Large things are usually obvious, small things are often hidden. In space, the opposite can be true. The most massive components of the universe may be invisible, while bright objects draw attention despite being relatively minor contributors to the overall mass. Time adds another dimension to size. Some things are big because they last. A short-lived explosion can be brilliant and intense, yet fleeting. A slow-forming structure can quietly persist for billions of years. Longevity becomes a kind of scale. Something that endures through most of cosmic history exerts a different form of bigness than something that appears briefly and vanishes. Influence brings these ideas together. Influence asks not how large something looks or how heavy it is, but how much it affects its surroundings. A massive cluster of galaxies can alter the motion of others across enormous distances. Its influence stretches far beyond its visible core. In this sense, big becomes relational. It depends on what else is nearby and how strongly it responds. At this point, the word big begins to feel less like a single label and more like a collection of questions. Wide compared to what? Heavy relative to which standard? Influential over what distance? Visible to which instruments? Stable for how long? This is not a flaw in scientific language. It is a reflection of reality. The universe is layered, and so are the ways of describing it. Scientists choose definitions not because they are perfect, but because they are useful for a given problem. When studying gravity, mass matters most. When mapping structure, extent and distribution take priority. When observing distant objects, visibility defines what can be known at all. There's a gentle humour in how often these definitions collide. A student might ask for the biggest object, only to discover that the answer changes depending on which textbook is opened. Not because the textbooks disagree, but because they are measuring different things. It is less like a disagreement and more like describing the same landscape from different viewpoints. Preparing for multiple answers is not about lowering standards or avoiding clarity. It is about gaining precision. The universe does not offer a single scale against which everything can be measured. It offers many, each revealing something different. Big can mean wide. It can mean heavy. It can mean old. It can mean influential. Sometimes it means all of these at once. Often it does not. Once this is accepted, the question of the biggest thing begins to change shape. It becomes less about finding a champion and more about understanding categories, less about ranking and more about context. The answer stops being a name and starts becoming a framework. And with that shift, the universe becomes easier to sit with. Not because it shrinks, but because the need to force it into a single definition quietly fades. When thinking about the biggest things in the universe, it is natural to begin with objects that still feel familiar. Planets, stars, things that can be pictured as individual bodies moving through space. They may be unimaginably large by everyday standards, but they still feel like objects in the same category as Earth: solid, bounded, and self-contained. Among planets, size already stretches intuition. Gas giants dwarf rocky worlds, spreading vast atmospheres around relatively small cores. Some planets discovered beyond the solar system are larger than anything orbiting the Sun, swollen by heat and proximity to their stars. Even so, planets remain modest by cosmic standards. They are large in a human sense, but they barely register once the scale begins to widen. Stars change that feeling quickly. A star is not just larger than a planet. It is a different kind of thing entirely. It is a self-sustaining sphere of hot gas, balanced delicately between gravity pulling inward and energy pushing outward. Because that balance can take many forms, stars vary enormously in size, mass, brightness, and lifespan. Some are small, dense, and long-lived. Others are enormous, unstable, and short-lived on cosmic timescales. This variation is why stars often become the first serious candidates for the biggest thing. Some stars are so large that if placed at the centre of the solar system, their outer layers would extend beyond the orbits of multiple planets. Their surfaces would not be solid, but diffuse and glowing, fading gradually into surrounding space. These stars feel vast in a way that planets never do. Red supergiants are the most dramatic examples. They represent a late stage in the life of very massive stars, when fuel in the core begins to change and the outer layers expand outward. The result is a star with a relatively cool surface temperature, giving it a reddish colour and a size that can be difficult to comprehend. These stars can be hundreds or even over 1,000 times wider than the Sun. At first glance, such stars feel like obvious answers. They are enormous. They dominate their surroundings. They contain vast amounts of matter. If the question is asked casually, it is tempting to stop here and declare the problem solved. Yet even here, the universe complicates matters. Despite their immense size, red supergiants are surprisingly tenuous. Their outer layers are spread thin, so thin that if the same material were compressed into a smaller volume, it would feel almost empty. This means that while their physical size is staggering, their mass may not scale in the same way. Some red supergiants outweigh the Sun by many times, but not by thousands. Size and mass diverge again. There is also the matter of definition. Where does a star like this actually end? Unlike a planet, a star does not have a surface you could stand on. Its edge is defined by a gradual thinning of gas. Measurements depend on where astronomers choose to draw the boundary, often based on brightness rather than substance. Change the definition slightly, and the size changes too. Even taking generous measurements, stars remain single objects. They are vast but isolated. One sphere of matter bound tightly by its own gravity. In the context of the universe, this becomes limiting. No matter how large a star grows, it occupies one location. It does not span regions of space in the way larger structures do. There is also time to consider. The larger stars live fast and die young. Red supergiants burn through their fuel quickly, shedding mass through powerful stellar winds and eventually ending their lives in dramatic explosions. Their enormous size is temporary, a brief phase in a much longer cosmic story. Bigness, in this case, is fleeting. This is one reason astronomers do not linger long on stars when discussing the largest things in the universe. Stars are impressive, but they're also individual and transient. They do not define the large-scale structure of space. They are building blocks, not frameworks. Planets fall away first, stars follow soon after, not because they are unimportant, but because they are too local, too compact, too singular. Once this shift happens, attention naturally begins to move outward, from individuals to collections, from single objects to systems. Stars gather into groups. They orbit shared centres of gravity. They influence one another over long periods of time. Patterns begin to emerge that no single star could create on its own. This transition feels subtle, but it is crucial. It marks the point where the question of size stops being about the dimensions of an object and starts being about how objects relate to one another, how far their influence reaches, how much space their collective presence shapes. There is a quiet logic to this progression. If the goal is to find the biggest thing, it makes sense to follow gravity outward, to ask not how large one object can become, but how many objects can be bound together into something larger. Stars naturally lead to this question because they rarely exist alone. They form in groups, they travel in families, they trace invisible structures that stretch far beyond their glowing surfaces. So while stars may feel like giants, they're only the beginning of the story. They're impressive, luminous, and dramatic, but they're also stepping stones. Familiar enough to anchor intuition, yet limited enough to encourage the mind to keep moving. The universe, as it turns out, has little interest in stopping at individuals. A single star can feel complete on its own, a bright centre, a source of heat and light, a body with a name and a place in the sky. But in reality, stars rarely exist in isolation. Gravity encourages company. Matter gathers. Motion settles into patterns. And before long, a star becomes the centre of a system rather than a lone point of light. A star system begins with gravity doing what it always does. It pulls. Any material that forms near a newborn star, dust, gas, leftover debris, feels that pull. Over time, some of that material gathers into planets. Some remains as smaller bodies, asteroids, comets, icy fragments drifting along wide paths. All of it participates in a shared gravitational dance, bound together not by physical contact, but by motion and balance. At first glance, the idea of a star system feels tidy. One star, a set of planets, clear orbits, clean diagrams. Yet even here, the universe resists neat boundaries. Because gravity does not stop at the last planet. It does not switch off beyond the outermost orbit. It fades gradually, stretching outward into space, growing weaker but never entirely disappearing. The influence of a star extends far beyond what is usually drawn. Long after planets are left behind, distant clouds of debris continue to feel the star's presence. These regions are sparsely populated, but they're still part of the system in a meaningful way. Objects there move slowly, tracing enormous arcs that can take millions of years to complete. From a distance, the system becomes less like a collection of orbits and more like a soft sphere of influence. This is where the idea of gravitational dominance becomes useful. Rather than asking where a system ends physically, astronomers often ask which object dominates motion in a given region. If a star's gravity primarily determines how nearby material moves, then that region can reasonably be considered part of the star's system. This definition is practical, but it is not sharp. Dominance fades gradually, not suddenly. Imagine ripples spreading across a pond. Close to where a stone enters the water, the ripples are strong and clear. Farther out they soften, overlap and blend into the surface. It becomes difficult to say where one ripple ends and the water simply returns to stillness. Star systems behave in much the same way. Their gravitational ripples extend outward, overlapping with those of neighbouring stars. And this overlap is not rare. Stars are born in clusters. They emerge from the same clouds of gas, forming near one another in both space and time. Early on, their gravitational regions mingle freely. Even later, as stars drift apart, their extended influences can still brush against one another across vast distances. The space between stars is not empty of interaction. It is filled with subtle negotiations between competing gravitational pulls. Because of this, star systems blur into stellar neighborhoods, regions of space where multiple stars share influence, exchange material, and shape one another's motion over long periods. These neighborhoods are not marked by fences or borders. They are defined statistically by trends in motion and density rather than by edges. This lack of hard lines is a recurring theme in astronomy. On Earth, ownership and boundaries are drawn sharply. Property lines, national borders, city limits. In space, boundaries are almost always fuzzy. They exist because they are useful approximations, not because the universe enforces them. Even the Sun, which feels like a clear centre from a human perspective, lives within a broader stellar environment. Nearby stars pass slowly over millions of years. Some drift closer, others wander away. Their gravitational fields overlap gently, like overlapping spheres of influence rather than isolated bubbles. The Sun's system is part of a much larger gravitational tapestry. This is where the idea of size begins to stretch again. A star system is bigger than a star, not because it contains more mass, but because it occupies more space. Its reach is defined not just by matter, but by motion. Its size depends on how far its influence remains relevant compared to that of its neighbours. In this sense, systems are already less object-like than stars. They are patterns rather than things, relationships rather than bodies. A system exists because many parts agree, over long time scales, to move in compatible ways. Remove gravity, and the system dissolves. Remove time, and it never forms. This shift matters for the larger question of scale. If bigness is about influence rather than appearance, then systems feel like a step towards something larger and more interesting. They suggest that size is not only about how much matter is present, but about how far order extends. Yet even systems have limits. Their dominance weakens. Their membership becomes uncertain. At some distance, the pull of another star becomes comparable. Motions change. Orbits loosen. What was once clearly part of one system begins to feel shared. This ambiguity is not a flaw. It is a feature of how gravity works across large distances. Gentle humour finds its place here. Humans often crave clear answers. Where does this system end? Where does the next begin? The universe replies with a shrug and a gradient. Not here, not there, somewhere in between, depending on how closely you look. As systems overlap, something else becomes apparent. Stars do not merely coexist. They form populations, groups with shared motion, streams of stars moving together through space. These groupings are larger than individual systems, yet still bound by gravity on broader scales. The idea of neighbourhood expands again. At this point, it becomes clear why astronomers do not stop with systems when discussing the largest things. Systems are important. They host planets. They shape environments. But they are still local. Their influence, while extended, is limited compared to the structures formed when many systems are considered together. Gravity encourages hierarchy. Small objects bind into larger ones. Those larger ones interact, forming patterns that extend farther still. Systems naturally invite the next question. If stars gather into systems, what do systems gather into? The answer does not arrive abruptly. It emerges gradually, as the scale widens and individual stars lose their identities. What matters next is not which star dominates a region, but how thousands or millions of them move together through space. The borders soften again, the ripples overlap more densely, and the universe begins to look less like a collection of separate systems and more like a connected whole, threaded together by gravity on scales far beyond any single star's reach. As individual star systems begin to blur together, a new kind of structure comes into focus. not a single star, not a small neighbourhood, but something vast enough to gather billions of stars into a shared, long-lived arrangement. This is where galaxies enter the picture. A galaxy is, at its core, a gravitational agreement, an immense collection of stars, gas, dust, and other material, all moving together through space, bound by a shared gravitational field. Unlike a loose stellar neighbourhood, a galaxy holds itself together on timescales that rival the age of the universe itself. Stars may orbit for billions of years without drifting away. Motion becomes organised. Patterns persist. What defines a galaxy is not simply the number of stars it contains, but the fact that those stars behave as a unit. They orbit a common centre of mass. They respond collectively to gravity. They form shapes that remain recognisable across immense stretches of time. A galaxy is not just a crowd, it is a system with memory. The number of stars involved is difficult to picture. Even smaller galaxies can contain millions of stars. Larger ones hold tens or hundreds of billions. Each of those stars may host its own system of planets and debris. The sheer multiplication of scale is staggering, yet galaxies manage to feel cohesive rather than chaotic. From a distance, they present themselves as singular objects, glowing softly against the dark. Galaxies also come in many forms. Some are graceful spirals, with arms winding outward like slow-moving pinwheels. Others are elliptical, smooth and rounded, with stars orbiting in many directions at once. Some are irregular, lacking obvious structure, shaped by past interactions or ongoing formation. Their sizes vary accordingly. A small dwarf galaxy might span only a few thousand light-years. The largest known galaxies stretch across hundreds of thousands of light-years. This variation can feel confusing at first. How can objects that differ so widely still share the same name? The answer lies in behaviour rather than appearance. Regardless of shape or size, galaxies act as coherent gravitational units. Their stars remain bound, their motions are correlated, their overall structure endures. At this point, galaxies begin to feel like serious contenders for the biggest thing. Compared to stars, they are enormous. Compared to star systems, they are vast beyond easy comparison. They occupy regions of space so large that even light takes tens of thousands of years to cross them. They contain enough matter to shape their surroundings over cosmic distances. Yet even here, appearances deceive. What is visible in a galaxy is only part of the story. The glowing stars and bright gas clouds that define its shape make up a surprisingly small fraction of its total mass. Surrounding every galaxy is a much larger invisible structure known as a halo. This halo extends far beyond the visible edges, enveloping the galaxy in a vast unseen presence. These halos are composed mostly of dark matter, a form of matter that does not emit or absorb light, but reveals itself through gravity. Astronomers infer its existence by observing how stars and gas move. Galaxies rotate faster than their visible mass alone would allow. Something unseen is holding them together. The halo matters because it dramatically changes the galaxy's true size. If size is defined by gravitational influence rather than light, then a galaxy is much larger than it appears. Its visible disk or core is only the bright centre of a much broader structure. The halo can extend several times farther than the stars themselves, reaching deep into surrounding space. This means that when galaxies are compared by size, the answer depends again on definition. Measured by light, one galaxy may seem modest. Measured by mass or extent of influence, it may be far larger than expected. The galaxy grows not by adding stars, but by revealing what was always there but unseen. Galaxies also refuse to remain alone. Despite often being described as islands of stars drifting independently through space, they exist within a broader context. Gravity draws them together into groups. groups assemble into clusters. Motion becomes collective once more, now on even larger scales. Even relatively isolated galaxies feel the pull of others over long periods of time. Their shapes bear the marks of past encounters. Distorted arms, streams of stars pulled away during close passes. Some galaxies merge completely, blending their stars and halos into a single larger system. Others merely brush past, exchanging material without fully combining. These interactions remind astronomers that galaxies are not static monuments. They are dynamic, evolving entities. Their sizes change, their shapes shift, their boundaries blur as material moves in and out. A galaxy today is not exactly the same galaxy it was billions of years ago, even if it carries the same name. This fluidity matters for the question of bigness. If galaxies grow by merging, then size becomes historical. The largest galaxies often owe their scale not to initial conditions, but to long chains of collisions and absorptions. Their greatness is accumulated, not inherited. There is a gentle irony here. Galaxies feel enormous and enduring, yet they are also temporary arrangements. Over cosmic timescales, they change. Some grow, some shrink, some are torn apart. Size is not a permanent title. It is a snapshot in a long story. Despite all this, galaxies remain a crucial step in the journey toward the biggest things. They mark the point where scale becomes truly cosmic, where numbers leave behind any remaining connection to everyday life, where individual stars fade into collective light. At the same time, galaxies subtly prepare the mind for another shift. They show that even the largest objects visible to telescopes are embedded in something larger still. Their halos overlap, their motions align, their distribution traces patterns across the universe. From far enough away, individual galaxies lose their identities. They become points in a much bigger arrangement. Filaments, clusters, voids. The universe begins to resemble a woven structure rather than a scattering of isolated islands. Galaxies invite this wider view without demanding it all at once. They are large enough to impress, but familiar enough to remain comprehensible. They bridge the gap between objects and structure, between things and patterns. In doing so, they gently encourage the next question. If galaxies gather together, if their halos touch and overlap, if their motions are coordinated on scales far beyond any single system, then perhaps the biggest things are not objects at all, but the frameworks that hold these islands together. The universe, once again, hints that scale is about connection as much as it is about size. As galaxies drift through space, gravity continues its quiet work. Individual islands of stars begin to feel one another's presence. Their paths bend gently, motions align. Over long stretches of time, galaxies gather into loose communities, no longer solitary, but part of something larger and more enduring. These communities are known as galaxy groups and clusters. A galaxy group is a modest gathering, often containing a handful to a few dozen galaxies bound together by gravity. They move through space as companions, orbiting a shared centre of mass. The distances between them are vast, far larger than the sizes of the galaxies themselves, yet their motions remain coordinated over billions of years. Clusters are the larger, denser relatives of these groups. Where a group might feel like a neighbourhood, a cluster resembles a sprawling city. Hundreds or even thousands of galaxies inhabit the same region of space, all held together by a gravitational field powerful enough to resist the universe's overall expansion, at least locally. These are among the most massive structures that gravity can assemble. What is striking about clusters is not how crowded they appear, but how empty they truly are. Even within a dense cluster, the space between galaxies is immense. Galaxies rarely collide directly. Most of the time, They pass one another at distances so large that individual stars never come close. A cluster is not a pile of galaxies pressed together, but a vast volume of space in which galaxies drift like slow-moving lanterns. This emptiness is misleading, however, because clusters are not made primarily of galaxies. In fact, stars account for only a small fraction of a cluster's total content. Most of the mass lies elsewhere, in forms that do not shine. One major component is hot gas. Between the galaxies in a cluster lies an enormous reservoir of gas heated to tens of millions of degrees. This gas does not glow visibly, but it emits X-rays, revealing itself to space-based observatories. It fills the cluster like a thin atmosphere, containing more mass than all the stars combined. Even this is not the dominant ingredient. The largest share of a cluster's mass is invisible. Dark matter forms an extended halo that envelops the entire cluster, binding everything together. Its presence is inferred through motion. Galaxies within clusters move too quickly to be held together by visible matter alone. Something unseen provides the necessary gravitational glue. This invisible framework gives clusters their longevity. Without it, galaxies would drift apart over time, pulled away by the expansion of space. Instead, clusters remain intact for billions of years. They are stable, long-lived features of the universe, surviving long after individual galaxies within them have changed shape, merged, or faded. From a distance, a galaxy cluster behaves like a single object. Its members orbit the shared center. Gas settles into a roughly spherical distribution. The cluster responds as a unit to external forces. Yet zoom in, and the complexity returns. Each galaxy follows its own path. Interactions occur. Material is exchanged. Structure exists on many levels at once. This layered nature makes clusters especially important when discussing size. They are not just bigger collections of galaxies. They represent a shift in how matter is organized. Gravity has scaled up. The patterns seen within galaxies repeat, but on far larger dimensions. Motions slow. Timescales lengthen. Change becomes gradual. Clusters also serve as laboratories for understanding cosmic history. Because they form from the densest regions of the early universe, their abundance and distribution offer clues about how matter behaved shortly after the universe began. Astronomers use clusters to test models of cosmic evolution, measuring how many exist at different distances and how massive they are. There's a quiet humour in how misleading appearances can be here. A cluster filled with hundreds of galaxies sounds crowded, yet most of its volume is empty space. A structure dominated by stars turns out to be governed mainly by things that cannot be seen. The biggest visible components are not the most important ones. This pattern repeats again and again in astronomy. Light draws attention. Gravity does the work. The sheer scale of clusters can be difficult to hold in mind. A cluster may span several million light-years. Light itself, moving at its maximum speed, would take millions of years to cross from one side to the other. Yet even at this scale, clusters are not the final word. They are not isolated monuments floating alone in space. Clusters themselves have neighbours. They sit along filaments of matter that stretch across vast regions. Their positions are not random. They trace the large-scale structure of the universe, marking the densest knots in a much larger web. Within this web, clusters grow by accretion. Smaller groups fall inward. Individual galaxies are drawn in over time. The cluster slowly increases in mass, not through dramatic events, but through steady gravitational gathering. This process continues for billions of years, making clusters among the most mature structures in existence. Because of their size and stability, clusters often feel like natural endpoints. Surely, it seems, nothing larger could hold together gravitationally. and in one sense, that intuition is close to correct. Clusters represent the largest objects that are fully bound by gravity in the present universe. Yet even here, the universe resists finality. While clusters are bound internally, they are also part of something larger that is not bound in the same way. Their arrangement across space reveals patterns that extend far beyond any single cluster's reach. Lines of clusters, sheets of matter, vast regions where clusters are rare or absent altogether. These patterns hint that bigness may not always mean being held tightly together. It may mean being arranged, correlated, shaped by initial conditions rather than ongoing gravitational bonds. Clusters thus occupy a pivotal position in the story of scale. They are enormous, massive, and long-lived. They are communities rather than individuals. They show what gravity can achieve when given time and material. At the same time, they gently point beyond themselves. Their existence raises a new question, one that feels almost inevitable. If clusters are nodes in a larger pattern, then perhaps the biggest things are not the nodes at all, but the structure connecting them. Once again, the universe invites the mind to widen its view, not abruptly but patiently, letting scale unfold layer by layer. When galaxy clusters are viewed one by one, they can feel like impressive endpoints, massive, long-lived, held together by gravity across millions of light years. Yet when astronomers step back even further, clusters themselves begin to look less like final structures and more like intersections. Dense knots in something much larger, stretched across the universe in subtle, repeating patterns. This larger arrangement is often described using the word supercluster, though the term can be misleading. A supercluster is not a single, tightly bound object in the way a cluster is. It is looser, more extended. Its members may share a common history and general motion, but they are not all held together by gravity in a permanent way. Over very long time scales, parts of a supercluster can drift apart. The structure is real, but its cohesion is gentle. Superclusters emerge when clusters are mapped across vast regions of space. Instead of appearing randomly scattered, they line up. Chains of clusters stretch across hundreds of millions of light years. These chains intersect at dense hubs and thin out into emptier regions. The universe begins to resemble a pattern rather than a collection. This pattern is known as the cosmic web. The cosmic web is the large-scale architecture of the universe. It is made up of filaments, walls, and voids. Filaments are long, thread-like regions where galaxies and clusters are concentrated. Walls are broader sheets of matter forming extended surfaces in space. Voids are the vast regions between them, where very little matter resides. Seen together, these components give the universe a structure reminiscent of foam or woven fabric. Dense strands surround enormous empty bubbles. Matter traces edges and intersections, leaving the centers largely clear. The image is not poetic exaggeration. Computer simulations based on physical laws produce patterns that closely match what telescopes observe. The emptiness here is not incidental. Voids are not simply leftover gaps between structures. They are essential parts of the pattern. Matter flowed away from these regions early in cosmic history, drawn towards slightly denser areas by gravity. Over time, the contrast sharpened. Dense regions grew denser. Empty regions grew emptier. The voids expanded, helping to define the shape of the web. This means that some of the largest features in the universe are defined by absence rather than presence. A void can span hundreds of millions of light years, yet contain only a handful of galaxies. It is big not because it is heavy, but because it is empty. Space itself becomes a structural element. Filaments, by contrast, are rich with activity. Galaxies flow along them slowly, guided by gravity toward cluster intersections. Gas streams through them, feeding star formation over billions of years. Dark matter forms the underlying scaffold, invisible but dominant, shaping the visible universe like a hidden framework. What makes the cosmic web especially striking is its scale. Individual galaxies vanish into points, clusters become beads along threads, even superclusters blur into extended regions rather than distinct objects. The universe stops looking like a place filled with things and starts looking like a single, continuous structure with varying density. Despite this vastness, boundaries remain uncertain. Where does one supercluster end and another begin? Where does a filament stop being a filament and fade into a wall? These questions rarely have precise answers. Definitions depend on thresholds chosen by researchers based on density, motion, or connectivity. Change the threshold, and the map changes slightly too. This uncertainty is not a failure of measurement. It reflects the nature of the structure itself. The cosmic web is not built from discrete blocks. It is a gradient. Matter thickens gradually in some regions and thins in others. Any line drawn is an approximation, useful but not absolute. There is something quietly calming in this realization. The universe does not rush to define itself sharply. It allows structures to emerge naturally, shaped by simple physical laws acting for immense spans of time. Gravity pulls, space expands, matter responds. The result is order without rigid edges. The scale of the web also reframes the idea of bigness once again. A supercluster may stretch across hundreds of millions of light-years, but even that is only a portion of a filament. A filament may run for billions of light-years, yet it is still just one strand among many. The largest structures begin to feel less like contenders and more like expressions of an underlying pattern. This is where the question of the biggest thing starts to loosen its grip. In the cosmic web, size is not about individual dominance. It is about connectivity, about how matter is arranged across the universe as a whole. The web itself does not have a single center or boundary. It fills the observable universe wherever matter exists. Gentle humor finds a place here too. If asked to point to the biggest thing, the universe seems to respond by handing over a map instead of an object. Not this, it says, but this arrangement. Not a thing you can circle, but a structure you can trace. The web also carries deep information about the universe's earliest moments. Tiny differences in density, present shortly after the universe began, were amplified over time by gravity. The cosmic web is the grown-up version of those early fluctuations, stretched and refined over billions of years. In this sense, the largest structures today are echoes of the smallest variations long ago. Because of this, the web is not static. It continues to evolve. Filaments slowly drain matter into clusters. Voids expand as space stretches. The pattern becomes more pronounced even as the universe grows larger overall. Change is slow but constant. At this scale, individual galaxies no longer feel central. They are passengers in a much larger flow. Their motions, histories, and interactions are shaped by where they sit within the web. Location matters. Context matters. Size becomes inseparable from environment. Superclusters, then, are not so much objects as landmarks within this greater structure, useful labels for regions of higher density, ways to orient within a pattern that has no sharp edges and no final scale. As the mind adjusts to this view, the idea of boundaries begins to soften. The biggest things are no longer those with the most mass or the widest span, but those that reveal how everything fits together. The universe appears less like a collection of isolated giants, and more like a single, intricately woven whole. And once that perspective settles in, another quiet question emerges. If even the largest visible structures dissolve into patterns, then where, if anywhere, does the idea of a biggest thing truly come to rest. As the map of the universe grows more detailed, certain regions begin to stand out. Long stretches where galaxies seem unusually concentrated, vast alignments that appear to run across enormous distances. When patterns like these are noticed, they often receive names, and once something is named, it has a habit of feeling more solid, more definite than it truly is. Some of the largest known cosmic structures entered astronomy this way. They were not discovered as single objects in the traditional sense. They emerged gradually as surveys of galaxies became deeper and wider. As astronomers plotted the positions of hundreds of thousands, then millions of galaxies, patterns appeared that seemed too large to ignore. Chains, walls, extended regions where matter appeared to be organized on staggering scales. Giving these regions names served a practical purpose. It allowed scientists to talk about them, study them, and compare them. A name becomes a handle, a way to point. But a name does not create a boundary. It does not turn a pattern into a solid object. It simply marks a region of interest within a continuous structure. Most of these enormous name structures were identified through galaxy redshift surveys. These surveys measure how light from galaxies is stretched as the universe expands, allowing astronomers to estimate distances. When plotted in 3 dimensions, the data reveal large-scale arrangements that are otherwise invisible. What looks like a smooth sky from Earth resolves into threads and sheets when depth is added. Yet these discoveries depend heavily on how the surveys are conducted. Every survey has limits. They observe certain regions of the sky, and not others. They detect brighter galaxies more easily than faint ones. They become less complete at greater distances. This introduces bias. Patterns can appear more prominent simply because they lie where observations are densest. Imagine shining a flashlight through fog. Where the beam is strongest, details appear. Where it fades, structure is harder to see. The universe is similar. Some regions are mapped with extraordinary detail. Others remain sparsely sampled. Name structures often emerge where data is richest, not necessarily where structure is strongest. This is one reason why boundaries remain uncertain. When astronomers outline a large structure, they must choose criteria. How dense must a region be to count? How connected must galaxies be to belong? Change the criteria slightly, and the structure grows or shrinks. Extend the survey, and new connections appear. The named region begins to look less isolated and more like part of a larger whole. There is also the question of scale. Some named structures span hundreds of millions of light years. Others appear to stretch close to 1 billion light years or more. Numbers like these are difficult to interpret intuitively. They feel enormous simply by comparison to familiar objects. Yet in the context of the observable universe, they still occupy limited regions. They are large features within a much larger framework. Debate naturally follows. Are these structures truly single things? Or are they coincidental alignments within the cosmic web? Are they coherent in any physical sense, or merely statistical patterns that appear significant when viewed from certain angles? Do they challenge existing models of cosmic structure, or fit comfortably within them once uncertainties are accounted for? Astronomers take these questions seriously. Large structures are tested against simulations of how the universe should evolve under known physical laws. If a structure appears too large or too orderly, it raises eyebrows, not because it must be wrong, but because it invites closer examination. Sometimes further data softens the claim, sometimes it strengthens it, often it complicates it. There is a gentle tension here between human perception and cosmic reality. Humans are excellent at spotting patterns. It is one of the brain's strengths. But that strength comes with a tendency to see coherence where there may only be gradual change. In the universe, structure rarely switches on or off. It emerges along gradients. It fades slowly into surrounding regions. Naming something can give the impression that a clear edge exists. In practice, most of these named structures dissolve at their margins. Galaxies become less concentrated. Filaments thin out. Walls fragment. Where one structure ends and another begins is often a matter of convention rather than physics. This does not make the names meaningless. They are useful markers. They help organize discussion. They allow scientists to test ideas about large-scale structure. But they should not be mistaken for rigid containers holding matter neatly inside. Uncertainty is not an inconvenience here. It is part of the process. Science advances not by locking in early impressions, but by revisiting them as data improves. Many of the largest named structures have been refined, redefined, or reinterpreted as surveys expanded. Some grew larger, others became less distinct. A few quietly faded into the background as broader context emerged. There is also a temporal element. These structures are observed as they were in the past. Light from distant regions has travelled for billions of years to reach Earth. What is seen is a snapshot from long ago. The universe has continued to evolve since then. Connections may have strengthened or weakened. Matter may have shifted along filaments. The present-day configuration is inferred rather than directly observed. All of this makes definitive statements difficult, and that is not a weakness. It reflects the scale of the problem. The largest structures push observation, theory, and imagination to their limits. They sit at the edge of what can be measured reliably. Caution becomes a virtue. Gentle humour can be found in how eagerly humans seek superlatives. The biggest, the longest, the most extreme. The universe responds by offering candidates, each with an asterisk attached, perhaps this one, depending on how measured, for now. Rather than providing a final answer, these name structures serve another role. They highlight how scale transitions from objects to patterns. They show that bigness, at the largest levels, is not about singular dominance, but about arrangement. About how matter traces the invisible scaffolding of gravity across immense distances. They also remind observers that knowledge grows unevenly. Some regions of the universe are understood in exquisite detail, others remain sketchy. What feels like a firm conclusion today may soften tomorrow as new data fills in the gaps. In this way, the largest named structures function as milestones rather than destinations. They mark how far observation has reached, not how far reality extends. They sit comfortably within uncertainty, inviting continued exploration rather than closure. By resisting definitive answers, they perform an unexpected service. They keep the question open, not as a problem to be solved once and for all, but as an ongoing conversation between data, theory, and perspective. And in that openness, the idea of the biggest thing begins to feel less like a prize to be claimed, and more like a lens through which the universe slowly reveals its complexity. As the scale widens further, something subtle but important begins to change. Structures that once felt tangible start to lose their edges. What could be pointed to, named, and outlined now becomes harder to isolate. Size no longer belongs to objects alone. It starts to belong to patterns. At these extreme scales, astronomers often speak in terms of statistical clustering. This does not mean guessing or hand-waving. It means recognizing that matter in the universe does not arrange itself into neatly separated units once distances grow large enough. Instead, it forms tendencies. Regions where galaxies are more likely to be found. Regions where they are rare. The structure exists, but it exists as probability rather than as a solid shape. This shift can feel uncomfortable at first. Humans prefer clear borders. A mountain has a base. A river has banks. A city has limits, even if they are debated. In the universe, once structures span hundreds of millions of light years, those instincts stop working. Density changes gradually, connections thin out rather than ending. What counts as part of something depends on how closely it is examined. Consider a cloud drifting across the sky. From a distance, it looks like a single thing. It has a general shape, a rough outline. Move closer and the edges fray. Wisps trail off. Portions fade into clear air. At no point does the cloud announce where it stops being cloud. Large-scale cosmic structures behave in much the same way. Another useful comparison is a coastline. On a map it looks like a line. Zoom in and that line becomes jagged. Zoom further and it becomes fractal, endlessly complex. The length of the coastline depends on how finely it is measured. The coast is real, but its exact boundary depends on scale. The universe inherits this same ambiguity when structures become enormous. Because of this, astronomers often disagree on classification, not because observations are poor, but because definitions must be chosen. How dense does a region need to be to count as a structure? How far apart can galaxies be while still belonging together? Over what distance must alignment persist before it is meaningful rather than coincidental? Different research groups answer these questions in different ways, depending on what they are studying. Some focus on gravitational binding, others on shared motion, others on statistical excess above background density. Each approach highlights different aspects of reality. None capture the whole picture on their own. This is where computer simulations become essential. Modern cosmology relies heavily on simulations that model the growth of structure over billions of years. Starting from tiny differences in density shortly after the universe began, these simulations allow gravity, expansion, and matter to interact under known physical laws. The resulting patterns can then be compared to observations. What emerges from these simulations is strikingly familiar. Filaments form, voids open up, clusters appear at intersections. The cosmic web grows naturally from simple beginnings. Yet even in simulations, boundaries remain soft. Structures overlap. Density thresholds blur. The universe resists being chopped into clean pieces even in a computer. Simulations also reveal why extreme size is so hard to define. Large patterns arise not because there is a preferred maximum scale, but because matter responds to gravity across all distances available. Small structures form first. Larger ones emerge later as matter flows along filaments. The process is continuous. There is no obvious place to stop. This continuity explains why astronomers can look at the same data and reach slightly different conclusions about what counts as the biggest thing. One may see a single immense structure. Another may see several connected regions that should be treated separately. Both interpretations can be reasonable, depending on the criteria used. Reality, it turns out, is messier than diagrams suggest. Textbook illustrations often show clean filaments and well-defined voids, separated neatly for clarity. In the real universe, transitions are gradual. Filaments branch and reconnect. Voids contain substructure. Clusters sit within clusters of patterns. The universe is textured rather than tiled. There is a quiet lesson here about scale and expectation. The farther out one looks, the less useful sharp categories become. At small scales, precision matters. At large scales, trends matter more than boundaries. Statistics become the language of structure. This does not mean that the universe becomes vague or unknowable. It means that knowledge takes a different form. Instead of asking where something ends, astronomers ask how likely it is to find matter here versus there. Instead of naming edges, they measure contrasts. Instead of counting objects, they study distributions. Gentle humour finds its place in this shift as well. Humans ask for the biggest thing. The universe responds with a histogram, not an object, but a curve, not a border, but a gradient. It is a polite refusal to play by simple rules. As structures become statistical, the idea of ownership fades. A galaxy may belong partly to one filament and partly to another. A cluster may sit at the edge of a void without fully defining it. Membership becomes fuzzy. Belonging becomes conditional. This fuzziness is not accidental. It reflects how gravity works over long distances. Forces weaken gradually. Influences overlap. There is no cosmic zoning authority assigning parcels of space. Everything negotiates continuously with everything else. At this stage, the notion of the biggest thing begins to dissolve, not because nothing is large, but because largeness no longer attaches cleanly to singular entities. It spreads across relationships. It lives in patterns that cannot be circled neatly. What remains is not confusion, but a quieter understanding. The universe is not built like a collection of boxes. It is built like a field, dense here, sparse there, structured but softly. Once this perspective settles in, the need for sharp borders begins to relax. Size becomes something to describe rather than something to crown. The question shifts again, not toward a new candidate, but toward a deeper appreciation of how structure itself emerges. And in that appreciation, the universe feels less like a puzzle to be solved and more like a landscape to be slowly explored. At a certain point, widening the view no longer reveals larger structures made of matter. Instead, it reveals a limit to what can be known at all. Not a physical barrier, not a wall or an edge, but a boundary defined by information. This is where the idea of the observable universe enters the story. The word observable is doing careful work here. It does not mean everything that exists. It means everything from which light or any other signal has had time to reach us. Observation, in astronomy, depends entirely on messages travelling across space. Light carries those messages. So does radiation at other wavelengths. If a signal has not arrived, then whatever produced it remains beyond reach, at least for now. This immediately explains why the observable universe has a size. The universe has a history. It has not existed forever. There was a beginning, a moment when space itself was far hotter, denser, and smaller than it is now. From that moment onward, light began travelling outward in all directions. Some of it has reached Earth. Some of it is still on its way. Some of it will never arrive. The observable universe is the region from which information has had enough time to travel to us since that beginning. It is not defined by distance alone, but by time and motion working together. Space expands, light moves. The two interact in ways that are not always intuitive. One detail often surprises people. The observable universe is much larger than its age might suggest. Although the universe is roughly 13.8 billion years old, the observable universe has a radius of about 46 billion light years. This is not because light travels faster than expected, but because space itself has been expanding while the light travels through it. A simple image helps here. Imagine dots drawn on a stretchable surface. As the surface expands, the dots move farther apart, even though none of them are moving across the surface themselves. Light behaves similarly. It travels through space, but space continues to stretch underneath it. By the time the light arrives, the source is much farther away than it was when the light began its journey. This expansion is gentle and uniform. There is no center, no preferred direction. Every region of space expands relative to every other. Galaxies are not flying through space away from us like debris from an explosion. Instead, the space between galaxies grows, carrying them along for the ride. Because of this, the observable universe is best thought of as a horizon. Not a physical boundary, but a limit of communication. Beyond that horizon, light has not had enough time to reach Earth. Those regions are not hidden behind anything. They are simply too far away in time as well as space. This distinction matters. The observable universe is not a container holding everything that exists. It is more like the portion of reality that has had time to say hello. Everything else remains silent, not because it is absent, but because its message has not arrived. There is no sharp edge to this horizon. It is not marked by a line or a wall. It is defined statistically by how far signals could have travelled under cosmic expansion. As time passes, the observable universe grows, slowly incorporating regions that were once beyond reach. Yet expansion complicates this growth. Some regions recede so quickly that their light will never arrive, no matter how long one waits. This introduces a quiet subtlety. The observable universe can grow while still leaving parts of the universe permanently unobservable. Not because observation fails, but because the geometry of space and time makes communication impossible. It is a reminder that limits do not always imply barriers. Sometimes they arise naturally from motion and scale. Importantly, this boundary is about information, not matter. Galaxies do not stop existing beyond the observable universe. Physics does not change abruptly. The laws governing matter and energy are believed to be the same everywhere. What changes is access. This is why astronomers are careful with language here. The observable universe is not the whole universe. It is the part that can, in principle, be studied. Everything beyond it remains speculative, not in the sense of being imaginary, but in the sense of being untestable with current or even future observations. There is a temptation to treat this boundary dramatically, to imagine standing at the edge of everything, to picture a final curtain beyond which nothing lies. But that instinct imports everyday thinking into a context where it does not belong. The observable universe does not end in a place. It ends in a condition. Beyond that condition, there may be more galaxies, more structures, more patterns similar to those already seen. There may be regions, much like the local universe, repeating endlessly. Or there may be variations, different densities, different histories current evidence cannot decide. And that uncertainty is not threatening. It is calm. The universe does not demand to be fully known in order to function. It does not require human awareness to continue unfolding. The observable universe provides a complete enough stage for understanding the laws that govern what can be seen. Those laws can then be extended cautiously beyond observation. In this sense, the observable universe becomes the largest meaningful boundary humans can discuss scientifically. Not because nothing lies beyond it, but because meaning in science depends on evidence. Where evidence cannot reach, claims must soften. There is something reassuring in this restraint. Rather than filling the unknown with speculation, science leaves space open. It acknowledges what can be said and what cannot. It allows the universe to be larger than comprehension without turning that fact into a problem. Gentle humour fits here too. Ask for the biggest thing, and the universe eventually answers with a horizon, not an object, not a structure, but a limit on conversation. It is as if reality says, this is as far as the discussion can go for now. Within that horizon, everything that has been described so far exists. Galaxies, clusters, filaments, voids, patterns layered on patterns. The observable universe contains all of them, not as a container, but as a shared history of light and time. Beyond it there is no reason to assume emptiness, only silence. And silence, in this context, is not absence, it is simply distance that has not yet been crossed, or perhaps distance that never will be. Either way, it invites a quieter response than awe or anxiety. It invites patience. The observable universe is not the biggest thing because it dominates everything else. It is the biggest thing because it defines the reach of understanding. It marks the boundary between what can be known directly and what must remain inferred. That boundary does not close the story, it keeps it open. In accepting it, the question of the biggest thing shifts once again, away from trying to outgrow the universe and toward understanding how far knowledge itself can extend. At this point, the most obvious answer finally asks to be addressed directly. If everything discussed so far exists within the universe, then why not simply say that the universe itself is the biggest thing? It feels clean, comprehensive, difficult to argue with. And yet, the moment this answer is examined closely, it begins to behave like all the others. It softens at the edges. The first complication is surprisingly basic. Is the universe even a thing? In everyday language, a thing is something that sits within a larger context. A mountain exists on a planet. A planet exists in a system. A system exists in a galaxy. Each thing is defined partly by what surrounds it. The universe, by definition, has no external container. It does not sit anywhere. It includes space itself. Calling it a thing stretches the word beyond its usual meaning. In physics and cosmology, the universe is better described as a totality. All space, all time, all matter and energy, all physical processes. This makes it difficult to compare the universe to anything else, because there is nothing outside it to serve as reference. Comparison requires contrast. The universe offers none. Still, size can be discussed in another way, not by asking what the universe is inside, but by asking how much of it exists. Is it finite or infinite? Does it have a total volume, or does it extend without limit? These questions sound abstract, but they arise naturally from observation and theory. Modern cosmology suggests that space is expanding uniformly. Galaxies move farther apart over time, not because they are travelling through space, but because space itself is stretching. Measurements of this expansion, combined with observations of the cosmic background radiation, allow scientists to model the overall geometry of the universe. Some of these models describe a universe that is finite but unbounded. Much like the surface of a sphere, which has a finite area but no edge, space could curve back on itself, travel far enough in one direction, and eventually you might return to where you started without ever encountering a boundary. In such a universe, size exists, but edges do not. Other models allow for an infinite universe. In this case, space extends endlessly in all directions. There is no total volume, no final scale, no biggest extent. Every region resembles every other on sufficiently large scales, and the observable universe becomes just one small patch within something vastly larger. Both possibilities are consistent with current observations. The universe appears very close to geometrically flat, which means that if it is finite, it is extremely large compared to what can be observed. If it is infinite, then the observable universe is an even smaller sample of a much grander whole. Present data cannot distinguish definitively between these options. This is where the idea of infinity enters the conversation. Infinity often feels like a place, somewhere far away, a direction you could point toward if only you travelled long enough. In mathematics, infinity is not a location. It is a concept, a way of describing something without limit. When cosmologists talk about an infinite universe, they do not mean a destination that could be reached. They mean that for any chosen distance, more space exists beyond it. There is no largest number that measures the universe's size, no final boundary to approach. Infinity describes a property of extent, not a region. This distinction matters because it changes how the question feels. If the universe is infinite, then asking whether it is the biggest thing becomes meaningless. There is nothing larger, but not because it dominates everything else. Because size itself no longer has an upper bound. If the universe is finite, the question becomes slightly more grounded but no less subtle. A finite universe could have a total size yet still lack edges. It could be complete without being contained. In that case, the universe would indeed be the largest possible physical structure, but not in a way that fits neatly with everyday notions of bigness. In both cases, humility becomes essential. Cosmology deals with scales so vast that intuition falters. Observations are limited, models are tested indirectly, conclusions are held lightly, ready to be revised as new evidence arrives. This is not uncertainty born of ignorance. It is caution born of respect for the limits of measurement. Scientists are careful not to claim final answers here. The history of cosmology offers many examples of confident statements, later softened or overturned. Each generation pushes understanding outward, only to discover new layers of complexity waiting beyond. There is something quietly appropriate about this. The universe, which contains everything, does not yield easily to summary. It resists being reduced to a single label. Even calling it the biggest thing feels slightly off, as if the language itself is too small. Gentle humour can live here as well. Ask whether the universe is the biggest thing, and science replies by asking what is meant by thing, by biggest, and by universe. The question multiplies rather than resolves, not out of stubbornness, but because clarity demands precision. Rather than closing the conversation, this moment invites a shift in perspective. Perhaps the question is not about identifying a final champion of size. Perhaps it is about understanding why such champions are difficult to name at all, why the universe keeps encouraging broader frames rather than singular answers. Seen this way, the universe being the biggest thing is both true and incomplete. It is true in the sense that nothing physical exists outside it. It is incomplete because size, as a comparative idea, loses meaning when there is nothing left to compare. Sitting with this openness does not require discomfort. It can be restful. The universe does not rush to define itself. It allows room for uncertainty, for multiple models, for quiet refinement over time. Knowledge grows not by claiming completion, but by remaining flexible. As the question loosens its grip, something else becomes clearer. The search for the biggest thing has never really been about size alone. It has been about orientation, about finding where understanding naturally comes to rest. And perhaps that resting place is not a final answer, but a reframing. A recognition that the universe is not a thing to be measured against others, but the context in which all measurement occurs. With that recognition, the question begins to change shape once again. The question of the biggest thing has a habit of changing, not because it is poorly asked, but because understanding itself is never still. Science does not advance by locking answers in place. It advances by revisiting them, gently adjusting their shape as new ways of seeing become available. One of the simplest reasons answers evolve is that instruments improve. Every major shift in astronomical understanding has followed a change in how the universe is observed. Early telescopes revealed moons around planets, and resolved stars as distant suns rather than points of light. Later instruments extended vision beyond visible light, uncovering structures made of hot gas, cold dust, and invisible mass. Each new window widened the frame. When telescopes grew more sensitive, galaxies multiplied. What once appeared as faint smudges became vast systems filled with structure. When surveys expanded, clusters appeared. When depth was added, filaments and voids emerged. The universe did not change. The view did. With each improvement, questions that once felt settled were reopened. What counts as a galaxy? Where does a system end? How large is a structure when its faint edges finally come into view? Answers shifted not because earlier scientists were careless, but because they were working with less information. Definitions evolve alongside instruments. Scientific terms are tools, not monuments. They're shaped to fit the problems being studied. When new phenomena are discovered, old definitions may stretch or be replaced. This is not backtracking, it is refinement. Consider how the idea of a galaxy itself has changed. There was a time when spiral galaxies were thought to be clouds within the Milky Way. Only when distances could be measured reliably did it become clear that they were entire systems far beyond it. The definition of galaxy expanded, and with it, the scale of the universe. The same pattern appears repeatedly. Structures once thought to be isolated are revealed to be connected. Objects once thought to be simple are found to have complex components. Boundaries once drawn sharply are softened as new data fills in the gaps. Historical examples show this clearly. The known size of the universe expanded dramatically in the early 20th century as distances to other galaxies were established. Later, the discovery of cosmic expansion reshaped ideas about space and time themselves. More recently, the recognition of dark matter and dark energy altered how mass and structure are understood on the larger scales. None of these shifts invalidated what came before. Each one placed earlier knowledge into a broader context. Earlier models were not wrong, they were incomplete. This gradual expansion of understanding is sometimes mistaken for uncertainty in the everyday sense. It can sound as though science is unsure of itself. In reality, it reflects a disciplined humility. Claims are limited to what evidence supports. When evidence grows, claims are adjusted. There is strength in this flexibility. A system that refuses to change in the face of new information quickly becomes brittle. Science remains resilient precisely because it allows its answers to move. The question of the biggest thing changes for the same reason maps change as they become more detailed. Early maps capture coastlines roughly. Later ones add bays, inlets, and subtle curves. The land was always there. The representation improves. Uncertainty in this context is not a flaw to be eliminated. It is a signal that the question sits near the edge of what can be known. At those edges, careful language matters. Overconfidence closes doors. Curiosity keeps them open. For the listener, this can be reassuring. It means that not knowing everything is not a failure. It is the normal state of inquiry. The universe does not demand complete understanding in order to be studied meaningfully. Partial views can still be accurate within their limits. Gentle humour finds a home here as well. Ask a scientist for a final answer, and you may receive a provisional one instead. Not because the scientist is evasive, but because experience has taught caution. Nature enjoys surprises. Maintaining calm continuity through changing answers requires patience. It means accepting that knowledge is layered, that today's explanation may be nested inside tomorrow's, that progress often looks like complication before it looks like clarity. The biggest thing question has survived precisely because it adapts. It absorbs new discoveries without breaking. It remains useful not as a riddle with a single solution, but as a guide for exploring scale, structure, and limitation. As instruments improve and theories mature, the question will continue to shift. New candidates will appear. Old ones will be reinterpreted. Boundaries will be redrawn. None of this diminishes what is already known. Instead, it reveals something quietly important. Science is not a collection of final answers. It is a process of listening carefully to the universe and adjusting descriptions accordingly. In that sense, the changing nature of the question is not a problem to solve. It is evidence that understanding is alive, responsive, and still unfolding. And with that recognition, the search for the biggest thing becomes less about reaching an endpoint and more about staying oriented as the view continues to widen. By this point, scale has grown very large indeed. Galaxies have blurred into patterns. Patterns have softened into horizons. The universe itself has entered the conversation, and somewhere along the way it becomes easy to feel that size carries weight beyond measurement. That bigger somehow means more important. This feeling is understandable. In everyday life, size often comes with consequences. Larger animals tend to dominate ecosystems. Bigger machines exert more force. Larger organizations influence more people. It is natural to carry that intuition outward, to assume that the largest things in the universe must also be the most meaningful. The universe does not seem to agree. In nature, size and significance are only loosely connected. Small systems can be extraordinarily complex. Large systems can be surprisingly simple. Importance depends on context, not scale. A single cell, for example, contains intricate machinery operating with remarkable precision. Chemical processes unfold in carefully regulated sequences. Information is stored, copied, and translated. Feedback loops maintain balance. All of this happens on a scale far too small to see with the naked eye, yet it is essential for life. Meanwhile, a vast region of empty space may stretch across millions of light years and do very little at all. The same principle applies throughout the cosmos. A modest star system can host planets with stable climates, complex chemistry, and long histories. A massive galaxy cluster, by contrast, may be dominated by hot gas and dark matter, evolving slowly and quietly over billions of years. One is not more important than the other. They simply play different roles. Astronomy reinforces this lesson repeatedly. Some of the most influential processes in the universe occur on small scales. Nuclear fusion happens in the cores of stars, not across entire galaxies. Planet formation unfolds within thin disks of dust and gas, not across clusters. Even the chemical elements that make up planets and living things are forged in specific stellar environments, not spread evenly through space. Large structures provide context. Smaller ones provide detail. It can help to think in terms of balance rather than hierarchy. The universe is not organized like a ladder, with importance increasing step by step as size grows. It is organized more like a landscape, with features of different scales contributing in different ways. Mountains matter, rivers matter, valleys matter. None replace the others. Everyday analogies can make this feel more familiar. A city depends on vast infrastructure, power grids, water systems, transport networks. But it also depends on small components, individual buildings, local streets, quiet routines. Remove any one layer and the whole system suffers. Size alone doesn't determine value. The same is true in physics. Fundamental particles are tiny, yet they determine the behavior of all matter. Physical laws operate uniformly, whether applied to a grain of dust or a galaxy cluster. The equations do not grow more important as the systems grow larger. They simply play out across broader canvases. This perspective gently removes emotional weight from comparisons of scale. Discovering that something larger exists does not diminish what is smaller. A planet does not become less interesting because a galaxy exists. A galaxy does not lose meaning because the universe may be far larger still. Even within astronomy, the most studied objects are often not the biggest ones. Stars similar to the Sun receive close attention because they are stable and long-lived. Planets of modest size are examined carefully because they are easier to characterize and more likely to host complex processes. Small does not mean trivial. Often, it means accessible. There is also stability to consider. Larger systems tend to change slowly. Their vastness smooths out variation. Smaller systems can respond more quickly, adapt more readily, and develop intricate structures. A small system can be dynamic in ways a large one cannot. This balance appears again and again. Large-scale structure provides the framework. Small-scale structure provides the activity, Neither dominates. Both are necessary. When scale is stripped of significance, something calming happens. The need to compare fades. The impulse to rank relaxes. The universe no longer feels like a competition of sizes, but a collection of interlocking processes, each appropriate to its scale. This shift is especially helpful as the topic moves toward emotional settling. Vastness can feel overwhelming when interpreted as hierarchy. When interpreted as diversity, it becomes gentler. There is room for everything. Gentle humour fits here too. The universe contains structures so large they defy intuition, yet it still runs on the same basic rules everywhere. No special treatment for the biggest things. No shortcuts. Gravity pulls. Energy flows. Time passes. Size changes, none of that. From this view, the question of the biggest thing becomes less pressing, not because the answer is known, but because its emotional charge is softened. Knowing that something larger exists does not threaten understanding. It simply expands context. Balance replaces comparison, coexistence replaces ranking. As pacing slows, it becomes easier to sit with this idea. The universe is not built to impress or intimidate. It is built to function. Scale is a consequence of that functioning, not a measure of worth. Smaller systems remain rich with detail. Larger systems remain impressive in scope. Each reveals different aspects of the same underlying reality. Neither needs to overshadow the other. With that perspective in place, the search for the biggest thing begins to quiet. The question does not disappear, but it loses urgency. It becomes something to explore thoughtfully rather than something to resolve. And in that quieter space, attention can begin to drift away from competition altogether toward a more settled appreciation of how all scales fit together. The universe does not ask to be ranked, it simply unfolds. It is easy to forget when thinking about enormous distances and structures that life unfolds quietly within them. Galaxies stretch across hundreds of thousands of light years. Clusters span millions. The observable universe reaches far beyond imagination. And yet, here on Earth, mornings still arrive on time, seasons still change predictably. The night sky turns overhead with gentle regularity. Humans live inside enormity without ever needing to confront it directly. This is not because cosmic scale is hidden, but because it is stable. The vast systems that shape the universe evolve slowly, on timescales so long that they appear fixed from a human point of view. The rotation of Earth, the orbit around the Sun, the steady rhythm of day and night, these motions are embedded within a much larger motions that change almost imperceptibly. The solar system moves through the galaxy. The galaxy drifts within a larger structure. That structure follows the expansion of space itself. All of this is happening continuously, yet none of it disrupts daily life. The forces involved are balanced. Motion is smooth. Change unfolds gradually. This stability is not accidental. It is the result of physical laws operating consistently across enormous spans of time. Gravity shapes orbits that repeat with remarkable precision. Energy flows settle into steady patterns. Systems that persist do so because they are balanced enough to endure. On human timescales, the universe is calm. Even events that sound dramatic when described in isolation occur so far away, or over such long durations that they barely register locally. Stars are born and die elsewhere in the galaxy, but the night sky looks much the same year after year. Galaxies merge over billions of years, but the stars within them continue their slow paths without sudden upheaval. Cosmic size does not translate into constant disruption. In fact, it often means the opposite. Larger systems tend to change more slowly than smaller ones. Their sheer scale smooths out fluctuations. Local disturbances are absorbed without consequence. Stability increases with size. This is why it is possible to live comfortably inside such a vast universe. The larger structures provide context, not interference. They set the background conditions under which smaller systems operate, then remain largely hands-off. Cycles play an important role here. Earth's orbit traces the same path year after year. The moon's phases repeat predictably. The sun rises and sets with reassuring consistency. These cycles are nested within larger ones, which are themselves nested within larger still. Each layer turns quietly within the next. Seen this way, enormity becomes a container rather than a threat. The universe is vast enough to allow countless systems to run independently, without crowding or conflict. There is room for regularity. Long timescales also soften perspective. The Milky Way completes a slow rotation over hundreds of millions of years. Galaxy clusters evolve over billions. The expansion of the universe unfolds across spans so long that they resist emotional interpretation. Against this backdrop, a human lifetime is brief, but not insignificant. It fits comfortably within the rhythms already in place. There is reassurance in knowing that nothing urgent is demanded by the universe's size. It does not require constant adjustment. It does not accelerate unexpectedly. It does not threaten to overwhelm through scale alone. Vastness in this context is passive. Even the laws governing the universe contribute to this sense of calm. Physical constants remain stable. Processes follow repeatable patterns. The same rules apply everywhere, whether in a distant cluster or a quiet laboratory on Earth. This uniformity allows prediction. Prediction allows trust. From the perspective of everyday life, cosmic size becomes almost irrelevant. The distances to distant galaxies do not affect the weather. The size of the observable universe does not alter the length of a day. The expansion of space does not pull objects apart locally. Gravity holds nearby systems together firmly enough that larger scale changes remain background noise. Gentle humour fits naturally here. Humans sometimes imagine that learning about cosmic vastness should feel unsettling. In practice, it mostly confirms how well things are already working. The universe has been large for a very long time, and life has managed just fine. This is not to say that change never occurs. On geological timescales, continents shift. On astronomical timescales, stars evolve. But these changes are slow, given systems time to adjust. Sudden disruption is rare. Continuity is the norm. Living inside enormity means inhabiting a small, stable pocket within a much larger, slowly changing whole. It means that daily concerns unfold against a backdrop that is vast but steady. The universe does not loom, it holds. As the pacing eases, attention naturally begins to drift away from the question of size and toward the feeling of placement. Not smallness, but situatedness. Being somewhere specific within something expansive, there is comfort in this idea. Enormity does not diminish the local, it supports it. It provides room for repetition, for habit, for long-term patterns to establish themselves. The night sky may hint at scale, but it does not intrude. The universe's size becomes something like a deep ocean beneath a calm surface, immense, ancient, and quietly present, while the surface continues its gentle motions. Knowing the depth exists does not disturb the waves. As emotional closure approaches, this perspective helps settle the mind. The universe is not rushing, it is not leaning in, it is not demanding response. It is spacious enough to allow life to proceed at its own pace. Humans function within vast systems not by confronting them, but by relying on their stability, by trusting that the rules remain consistent, by living within cycles that have been repeating long before any single observer noticed them. Enormity, when viewed this way, becomes less about scale and more about reliability, less about awe and more about assurance. The universe is large, yes, but it is also patient, and in that patience there is room to rest. After travelling through stars, systems, galaxies, clusters, patterns and horizons, there comes a natural pause, not because everything has been resolved, but because the urge to resolve begins to soften. The question that started the journey does not disappear, but it loosens its grip. What is the biggest thing no longer feels like something that must be answered cleanly. This is an important moment. Many questions in science are not designed to close neatly. They are designed to orient understanding, to provide a direction rather than a destination. The question of size, especially at cosmic scales, belongs firmly in this category. It opens perspectives, it invites comparison, it stretches intuition, but it does not require a final verdict. Science is comfortable with this kind of openness. In many areas it prefers ranges to endpoints, confidence intervals rather than single values, models rather than declarations. This is not hesitation, it is precision expressed honestly. When astronomers measure distances, they often give uncertainties alongside the numbers. When they describe structures, they speak in terms of likelihood and probability. When they model the universe, they explore families of possibilities rather than one fixed outcome. Reality is complex enough to deserve that care. The biggest thing question benefits from the same treatment. Depending on how size is defined, the answer shifts. Sometimes the observable universe feels like the largest meaningful boundary. Sometimes large-scale structure takes that role. Sometimes the universe as a whole enters the frame, though even that resists easy categorization. None of these answers cancel the others, they layer. Layered answers are not incomplete answers, they are answers that respect context. Comfort grows when this is accepted. The need to rank and finalize gives way to curiosity that is calmer and more patient. Instead of asking which answer wins, attention turns to why different answers exist at all. What each one reveals, what each one leaves open. This approach mirrors how science itself progresses. Questions are revisited rather than retired. Concepts are refined rather than replaced outright. Understanding deepens through accumulation, not through sudden closure. There is something quietly reassuring about this process. It suggests that knowledge does not require urgency. It unfolds over time, at a pace set by evidence rather than expectation. The universe does not mind being understood gradually. Gentle humour fits naturally here. Humans often ask questions as if the universe is waiting to hand over a final answer, neatly wrapped. In practice, it offers a collection of perspectives instead. Not an ending, but an invitation to look again from a slightly different angle. Letting the universe be big means letting go of the need to contain it in a single idea. It means accepting that scale can be described without being conquered. That understanding can be accurate without being complete. This does not diminish the value of knowledge, it enhances it. Knowing where explanations soften is part of knowing where they are strongest. Boundaries of understanding are not failures, they are landmarks. The language of ranges illustrates this well. When cosmologists talk about the size of the observable universe, they give approximate values, grounded in measurement and theory, yet open to refinement. When they discuss what lies beyond observation, they speak carefully, outlining possibilities without insisting on certainty. This restraint is not caution born of fear. It is confidence born of method. Layered answers also leave room for future insight. New instruments may extend observation, new data may sharpen models, concepts that feel settled today may be reframed tomorrow. By not insisting on finality, science keeps space open for growth. For the listener, this openness can feel restful. There is no pressure to memorize a single correct response, no need to hold on to a definitive conclusion. The question can remain alive, gently evolving as understanding does. Calm curiosity replaces urgency. Wonder remains, but it is quieter, more spacious, less demanding. At this stage, it becomes clear that the question was never only about size, it was about perspective, about how humans relate to scales far beyond everyday experience, about learning to think comfortably in layers rather than absolutes. Letting the universe be big also means allowing it to be unbothered by human categorization. It does not adjust itself to fit questions. It reveals itself gradually, according to laws that operate independently of how satisfying the answers feel. There is a subtle freedom in this. The universe does not require endorsement or completion. It does not need to be reduced to a final diagram. It continues, patient and expansive, whether fully understood or not. As this perspective settles in, the question of the biggest thing transforms. It becomes less about identifying an object or boundary, and more about recognizing a relationship. The relationship between observation and reality, between measurement and meaning, between curiosity and acceptance. This transformation does not close the journey. It prepares it to end gently. Rather than concluding with a declaration, the mind can rest with a sense of orientation, knowing how the universe is structured, knowing where definitions hold and where they blur, knowing that uncertainty is not an obstacle, but a natural feature of exploration. In this light, the biggest thing is not something to be captured. It is something to be approached with patience, something to be described from multiple angles, each adding texture rather than resolution. The universe is large enough to accommodate this approach. It does not demand haste. It does not reward oversimplification. It offers scale as context, not as a challenge. Letting it be big is an act of trust. Trust that understanding does not require closure. Trust that curiosity can remain open, ended without losing value. Trust that knowledge grows best when allowed to breathe. As the final reflective landing draws nearer, this trust becomes the lasting takeaway. Not an answer, but a posture, a way of holding questions gently without needing to press them flat. The universe remains big, bigger than any single description, bigger than any diagram, bigger than any answer that could be spoken aloud. And that is not a problem to solve, it is simply how things are. The question that began this journey sounded simple at first. What is the biggest thing in the universe? It felt like something that could be answered by pointing outward, by identifying a vast object or a distant boundary and letting the scale speak for itself. Yet along the way, the question quietly changed. It widened. It softened. It learned to ask something slightly different. Instead of demanding a single answer, it began to explore how answers depend on perspective, how size can mean width, mass, influence, duration, or reach, how some of the largest features in existence are not objects at all but patterns, how boundaries often reflect limits of observation rather than limits of reality. By the end, the question no longer asks for a champion of scale. It asks what scale itself can teach. One of the clearest lessons is that perspective matters more than absolute size. From one viewpoint, a star can feel enormous. From another, it becomes one point among billions. A galaxy can seem vast until it dissolves into a filament. A filament can feel immense until it blends into the observable universe. Each scale is real. None cancels the others. Understanding emerges not from choosing the correct scale, but from learning to move between them comfortably. This movement reveals something quietly reassuring. Partial understanding is still understanding. Knowing how something fits locally, even if its full extent remains unknown, is enough to make sense of experience. The universe does not require total comprehension in order to be meaningful. In fact, much of science operates exactly this way. Models describe limited domains. Theories apply within defined ranges. Knowledge grows by layering insights, not by eliminating uncertainty entirely. What matters is not having the biggest answer, but having an answer that works where it is used. This is especially true when dealing with something as vast as the universe itself. No single description can capture it fully. Every explanation highlights certain features and leaves others in the background. This is not a flaw. It is an honest reflection of scale. There is also a gentler lesson here about emotional response. Vastness is often presented as something overwhelming, something meant to provoke awe or insignificance. Yet the universe does not insist on that reaction. When approached slowly, scale becomes contextual rather than confrontational. Large structures unfold over immense timescales. Change is gradual, patterns persist. The universe feels less like a dramatic spectacle and more like a steady environment. Big does not mean urgent. It does not mean unstable. Often it means the opposite. This steadiness allows life to proceed quietly within it. Orbits remain reliable. Physical laws remain consistent. The same principles apply everywhere, from the smallest interactions to the largest arrangements. Scale does not disrupt continuity. It supports it. Even the limits of knowledge fit into this calm picture. The observable universe marks a boundary, not because reality ends there, but because information does. Beyond that horizon, the universe may continue, or it may not. Current evidence cannot decide, and that uncertainty does not weaken what is known within the horizon. Science is comfortable with this. It does not rush to fill silence with speculation. It acknowledges where understanding rests and where it must pause. This restraint is part of its strength. There is something quietly grounding about recognizing that not every question needs closure. Some questions are meant to remain open, not as unresolved problems, but as spaces for continued orientation. The biggest thing question turns out to be one of these. It invites curiosity without demanding finality. It encourages exploration without pressure. It teaches how to think, not what to conclude. Gentle humour can be found in how this unfolds. A question that seems to ask for a single enormous answer ends up offering many smaller insights instead. The universe responds not with a trophy, but with perspective. In that sense, the biggest thing is not an object or a structure. It is the framework within which understanding grows, the ability to hold multiple scales at once, to accept that some boundaries are defined by observation, to recognize that knowledge can be precise without being complete. This perspective leaves the listener grounded rather than awed, situated rather than diminished. The universe does not loom, it surrounds, steadily and without urgency. As this journey comes to rest, there is no need to summarize aggressively or to compress everything into a final statement. The ideas have already settled into place. Stars remain stars, galaxies remain galaxies, patterns remain patterns. The observable universe remains a horizon of information. Beyond it, the universe remains itself, whether known or unknown. Continuity is the lasting impression. The universe is not rushing toward an endpoint. It is not waiting for a final description. It unfolds according to its own rhythms, patient and unhurried. Understanding follows at a slower pace, and that is enough. In the end, the biggest thing teaches something simple and steady. That scale is contextual. That meaning does not depend on magnitude. That clarity can coexist with uncertainty. And perhaps most importantly, that it is possible to live comfortably inside a universe that is larger than any single answer, without needing to shrink it down to feel at home. The universe remains vast, understanding remains partial, and life continues quietly within both. Nothing more is required. The question that opened this journey never truly asked for a measurement. It asked for orientation, for a way to place understanding somewhere steady while everything else expanded outward. What began as a search for the biggest thing slowly became something else, a lesson in scale, a lesson in limits, a lesson in how the universe prefers patterns over prizes, ranges over endpoints, and patience over finality. Along the way, size stopped behaving like a competition. Bigger did not replace smaller, larger did not erase nearer. Each scale revealed something different, and none of them claimed authority over the rest. Stars mattered where stars mattered. Galaxies mattered where galaxies mattered. Patterns mattered where individual objects dissolved into structure. The universe did not offer a single answer because it did not need to. It offered context instead. This is one of the quieter strengths of scientific understanding. It does not insist that every question resolve into a sentence that can be underlined and closed. It allows some questions to remain open, not as gaps in knowledge, but as spaces where perspective can settle. The observable universe marks a boundary of information, not of existence. Beyond it, reality may continue in familiar ways, or in ways that differ subtly or profoundly. The evidence does not yet decide, and the undecided space does not diminish what is already known. It simply reminds that understanding grows outward, not all at once. What matters most is that everything needed for clarity already exists within reach. The laws that govern distant galaxies are the same laws shaping the quiet motion of Earth. The forces that arrange the cosmic web also keep familiar systems stable and predictable. Scale does not interrupt continuity, it preserves it. The universe is vast, but it is not urgent. It does not rush explanations. It does not demand conclusions. It unfolds steadily, allowing understanding to follow at a human pace. That may be the most grounding lesson of all. The biggest thing is not something that needs to be named, circled, or finalized. It is the recognition that reality is layered, that knowledge is contextual, and that partial understanding is not a failure. It is the normal, healthy state of curiosity. Nothing here asks to be resolved tonight. Nothing needs to be settled before rest arrives. The universe will remain large tomorrow, and the next day, and long after any single question has faded. Understanding will continue, slowly, carefully, one layer at a time. For now, it is enough to know that scale does not diminish meaning, that uncertainty does not erase clarity, that vastness can be calm. The universe is big, understanding is ongoing, and there is room for both.